Greetings, everyone. Today, Team 2 is going to present about real-time trend analysis pipeline for Spotify. Let's meet our team. I am Chanakya Samsani, serving as business analyst, Bikram Chanda as our data engineer, Sai Charan as DevOps engineer, and Chetan as ML engineer. Our objective is to design a scalable and robust data engineering pipeline for real-time trend analysis of Spotify streaming data. Coming to our business questions, our first target is to answer how to safeguard business data and ensure cybersecurity and what specific measures are being implemented. And next, what are the latest emerging trends in business and how can we strategically leverage them for growth and innovation? We propose that we would be implementing encryption, multi-factor authentication, and continuous monitoring to fortify our cybersecurity framework and utilizing personalized content, AI-driven recommendations, and interactive user experiences to enhance business performance. Now, my friend Charan is going to tell about our approaches.
Thank you, Chanakya. Our approaches include mainly CRISP-DM methodology and general data pipeline. CRISP-DM, which stands for Cross-Industry Standard Process for Data Mining, provides a structured framework for data mining projects comprising business understanding, data preparation, modeling, evaluation, and deployment phases. A data pipeline is a series of processes that moves data from source to destination, facilitating its processing and analysis, which encompasses 4 main stages, which are ingestion, storage, processing, and visualization or analysis. I'll pass over the mic to Chetan so that he can give you a deeper understanding of our data pipeline.
Got it, Charan, thanks. Spotify API trees track data including title, artist, and popularity. Python executes custom code for Spotify API interaction and data handling. Amazon CloudWatch triggers hourly Python code for data updates. AWS Lambda processes track data efficiently with Python functions. Kafka Streams track data in real time for further processing. S3 Bucket stores raw and processed track data. Apache Spark processes large track data volumes effectively. Crawler automatically infers track data structure. AWS Glue manages data catalog for easy querying. Athena runs SQL queries for insightful analytics on track data. Plotly visualizes Athena query results for easier interpretation. Let's see the video demo given by our data engineer Bikram Chand.
We achieved the data pipeline that we have shown earlier by using AWS services, Kafka, and the Plotly in this project. For the data ingestion part, we fetch the track information from the Spotify API. This is achieved using a Python script designed to interact with the Spotify API endpoints. The code looks like this. And to ensure continuous and timely data retrieval, the Python script is integrated with Amazon CloudWatch events. We have created the CloudWatch events named Spotify Trigger API. For executing the Python script in a serverless environment, we have used the AWS Lambda services. So our Lambda functions looks like this. And also, as you can see, Amazon CloudWatch events that we have created earlier is attached to it. It means that this Lambda function will execute in every 1 hour. So to execute this Lambda function, I'll click on the test button. So once this code is executed, this will send each data fetched from the Spotify API to the Kafka server. Our Kafka server is running in our EC2 instances, and as you can see, the Kafka consumer is consuming the data here. Now it's time to store this coming data into the S3 bucket. To do that, we have a consumer Python file in our EC2 instance. I'll just run this file. This Python file will make sure all the data coming from the Spotify API will be stored in a JSON format in the S3 bucket. So as you can see, we have more than like 4,000 JSON data inside our S3 bucket. In our data processing pipeline, after storing the raw data in an S3 bucket, we leverage Apache Spark running on an EMR cluster with a Zeppelin notebook for comprehensive data processing. Within the notebook, we read the JSON files and undertake various processing steps, such as like dropping the duplicates and addressing null values and many more. And after that, once the data is cleaned, we transform it into a CSV format and save the refined dataset back to the S3 bucket. To save the output, we have created a new S3 bucket called Spotify output dataset, where the CSV file will be stored. As you can see here. For further analysis, we convert the CSV data into a structured table schema using AWS Glue, employing a crawler to catalog the schema and create a data catalog. So as you can see here, we have created a crawler which is called Spotify crawler. Along with this, I have created a database, which is Spotify Tracks DB. Within this, I have a table named output. This we will use to seamlessly query the data using SQL through the Athena. Let's go to the Athena. So in the Athena, I have selected the database I've created in the Glue, and here I will fetch the top 10 artists, album, and the tracks using the SQL queries. Here is the SQL query, and the results of these SQL queries are then visualized using Plotly, allowing us to gain insights from the data. So this is how our dashboard looks like. It was created using Plotly and Dash. It is running in the EC2 server. So the dashboard contains the visualization like top 10 artists by popularity, top 10 artists by number of tracks, top 10 songs by popularity, best album by average popularity, top albums by popularity, popularity over time, top tracks by popularity, top artists by popularity. And down here, we also have a artist dashboard from where you can select the specific artist from the drop down. And once you select it, it will show all the songs sang by the artist as well as along with its popularity.
Thank you everyone for listening. Feel free to shoot us with your questions.